I want to start with chapter 5, but from our book. I want to show you a couple of things from our book, and I definitely recommend you to read our book because I realized that students are not reading the book. Okay, lectures are okay, but reading the book is maybe the easiest way and the best way to learn the topic. You can, I would recommend you to go through reading of the book, and then watching the video, and then start solving some problems, because if you get used to reading books, learning from books, this is going to be a big plus for your future. Whatever things that you are interested in learning, you would just refer to the book and read it from it. Okay, this is very important. Of course, watching the lectures are also useful, but I strongly recommend you to read the book. Okay, so in section 5.1 we are gonna talk about areas, how to find the areas. In ancient times, people didn't know how they wanted to compute the areas because of some farming and some economical issues. They had to learn how to calculate the area of their field. Okay, so they had to do it. So they came up with, of course, Riemann put it in very formal ways, but people thought of these finite sums, estimating the area by using finite sums. For regular shapes like triangle, circle, or a square or rectangle, it's easy to find the areas, but for regions such as this, calculating the area is not as easy. So we start with this example, y is equal to 1 minus x squared, and we are going to, instead of finding the exact area, we want to estimate the area, because this is the first step to get to the exact area. You cannot get to the exact area right away. First you need to know the best way to approximate the area, get an estimate for this area, and then from it Riemann came up with some formulas, the limit of some formulas, and we call it a limit of the Riemann sum to get the exact area from it. Okay, so step by step. So first we are going to learn how to estimate this. So the first example we are going to encounter is y is equal to 1 minus x squared. We are going to go through that, and as you would see, I want you to just look at these roughly. You see this is the same function, the blue one, y is equal to 1 minus x squared, but the way we approximate is we are just forming some rectangles on top of them, and just calculating the areas of rectangles, because we know how to calculate the area of the rectangle, right? Length and width, length times width is the area of the rectangle. So even if the area that we find is going to be bigger than the original area, but that's good, that's an estimate. Another thing I want to get your attention is, if you if you form thinner and thinner rectangles, you get a better approximation. Like the approximation on the right is going to be a better area approximation than the one on the left, because number of rectangles that you use to approximate the area is 2 on the left. The number of rectangles you use to estimate on the right is 4. As you see, we have less pink areas here, which are actually excessive areas here, but if you look at the left side, the pink areas, which are the excessive areas, are more than this. So if you have more and more rectangles when you're approximating, it is the best, it is much better, I should say. So this is a rough idea. We are going to show you how to do these later on, and let me go through all of the section, couple of just to show you. So these are the details how we calculate estimate the area, but sometimes there are actually 3 ways I want to tell you that we can use to estimate the areas. We can build these rectangles underneath the curve, or we can build these rectangles just by using a midpoint in here, which is gonna have, at the end we are gonna have like half of it inside the region, half of it outside the region for each rectangle. I mean, not exactly half, but some part of it, I should say. And this is another method. This is in the first one we use the left point of the subinterval to get that And then we this is the midpoint rule, the one on the right, and we have the another one which we had just seen in the previous page, which is approximating areas in a way that the rectangles are gonna the excess area is gonna be outside. Okay, so all right, so let's go down. See, we have, so they are saying about the midpoint rule here. Do you see that? So we are going to talk about that too. Do you see that the rectangles are thinner and thinner, and this is the left endpoint we used here, left endpoint to get that. It's not the midpoint. See, we have less excessive points areas here, the blue areas, because we have thinner and thinner. We have lots of rectangles to approximate with. This one we use the right end point in this case. Left end point in this case. Let me see just a sec. I'm gonna tell you. Right hand point. This one is the right hand point. This is the left hand point we use. So the excess areas are outside the exact region. Here in the previous one, the excessive areas are inside the region, right? Because we call this actually underestimate. This is called the overestimate because the estimate is more than the exact area. This is called the underestimate because the estimate is less than the exact area. So we are going to talk about that. And let's see. Let me see. We have some. We can easily see. Look. What we do is, in order to form our rectangles, we form sub-intervals. So the more sub-intervals you have, the more rectangles you have. Okay, so see, number of sub-intervals, if it is 2, we have the lower sum, which means lower estimate. This is the midpoint sum estimate, and this is the upper sum estimate. So we get all these numbers. But as you increase the number of sub-intervals to 1000, these values gets very close to each other. Although at the very beginning, when you have less rectangles here, which means less sub-intervals, sub-intervals is the same as rectangles you form. Sub-intervals correspond to the width of the rectangle that you're going to form. If you have 2 sub-intervals, you have 2 rectangles. If you have 4 sub-intervals, you have 4 rectangles, etc. So these are the 3 different ways to approximate the exact area. Okay. Again, as you increase the number of rectangles, these approximations, these estimates are going to be very close to each other, as you will see 0.6666. Okay, we are going to talk about that as well. Let me see. This is another application where we use this integration for distance traveled. Because if you remember, we learned in previous chapters that if you have a position function, if you take the derivative of it, you get velocity function, and then if you take the derivative of the velocity function, you get the acceleration function. Now, when we sometimes you would see that we would be given acceleration, but they are going to ask us to find velocity, so we are going backwards, or they are going to give us the velocity function and they are going to ask us to position function. If this is the case, then instead of derivative, we have to do the antiderivative, okay, because we are going backwards. So in that case, so we are going to calculate the region underneath the curve, which is actually integration in some sense. Since we don't know yet how to do the integration, we are going to just estimate the area underneath the curve, and the area underneath the curve is going to give us the, for example, velocity. If the if the graph belongs to acceleration, it's going to give us the position if the graph is given as the velocity, okay? So these are just applications of what we are going to be learning about the estimation. Let's see what else we have. Okay, this is this is an application to travel distance estimates. If the number of subintervals, or in other words, the number of rectangles that you're going to use to estimate under the graph, and of course in each time the length of subinterval is going to change, because the more rectangle means the length of the subinterval is going to be smaller and smaller. And upper sum and lower sum, as you will see, is you have 192 rectangles. The upper sum and the lower sum, they are very close to each other. So we are going to see that too. Okay. And then, yeah, there's this displacement versus distance traveled. This is an important notion too. I'm going to talk to you about that when we get there. Tell you more details about that. And then let's see. Now this is about the that thing. So, and there's an average value of a non-negative continuous function. And if we have time, we are going to also talk about that as well. Okay, it's also related. Roughly what you do is the average value of a function g on an interval a is going to be the area underneath the curve divided by the length of the b minus a. Okay, this notion is going to be coming from if you choose a straight like the constant function. If you want to find what's the average of this constant function, of course c, but how do you get that? Actually, you find this area underneath, which is the rectangle area. If you divide by b minus c, you get c as an answer. So we use this idea to get the average value of a function for a curved for a curve like this, not a straight line. Okay, so this is going to give us the average value of g. So in the average, how does this g, or what type of value does this g take? That's going to be an answer to that. And let's see, here's a question: estimate the average value of the function f is equal to sine x on the interval 0 to pi, is an example to that. And we have a summary at the end. Excuse me. And we have some problems to solve.